students. So we were doing Euclidean spaces, and so let me tell you once again what is an Euclidean domain. So an integral domain R is said to be Euclidean domain if there exists a function delta which satisfies Euclidean algorithm, which is the third point. It should be non-negative, and delta of AB should be always greater than equal to delta of A. Then the integral domain with this delta will be called Euclidean domain. Okay, so we saw a few examples. A ring of Gaussian integer is one of the example. So integers is the simplest example you have. Then a ring of polynomials over a field. So delta can be taken as degree. So that is also a good example of Euclidean domain. Okay. So this delta is called a valuation. Okay. So this delta is called a valuation map. Next, let me write this proposition. So let R be a Euclidean domain with valuation map delta then for a non-zero u is a unit if and only if the delta of u is equal to delta of 1. Okay. Second is delta A is equal to delta of AB if and only if B is a unit and AB are here non-zero. Okay, both are non-zero. Third, if A is associated to B, then the valuation is same. Fourth, if valuation is same and one of them divides other, then both are equal, both are associates. A is associated to B. So you don't have exact converse of third part, but if you have one more condition, that is one divides another, then you get associativity. Now fifth is converse of 3 is not true. There exists A, B belongs to R such that delta A is equal to delta B, but they are not associates. A is not associated to B. Okay. So let us try to see these examples, these points. Okay. Now U is a unit. So first point, U is a unit, which implies there is some B belongs to R such that UV is equal to 1. Okay. This clearly tells you that delta of UV is equal to delta of 1, that has to be greater than delta U. Okay. That is the second point of second property of valuation. Also, delta of U can be considered as delta of U into 1 So that is greater than equal to delta of 1. Okay. So delta of u is equal to delta of 1. Converse part, conversely, if delta u is equal to delta 1, then just write 1 as a qu plus r. Okay, such that either r is 0 or delta r is less than delta u. Okay, which is equal to delta of 1. Okay, this is it. Now if r is 0, then we are done. Okay, then 1 is u is a unit. If r is 0, then we are done, because so suppose r is non-zero, therefore del r has to be less than del of 1. But again, del r, which is can be written as del r into 1, which is equal to delta into 1. Okay, so you get contradiction. Therefore u must be a unit. U must be a unit. Okay, so that is the first point. Let's see second. Second key है कि del A is equal to del AB if and only if B is a unit. Now this is again clear. So del A is equal to del AB given. So let del A is equal to del of AB. Now by Euclidean algorithm, there exist Q and R such that A can be written as Q times AB plus R. Okay, such that R is 0 or del R is less than delta of AB. So we have to prove that AB is a unit. Again, if R is 0, then by cancellation law, you will get 1 is equal to QB, which implies B is a unit. Okay, so suppose del R is less than del of AB, but del of AB, which is equal to del of A, which can be written as del of A into which is less than equal to, so del of A into, so R is equal to A into 1 minus QB. Okay, from here. So we will try to make this as R. Del of AB is equal to del of A, which is less than equal to del of A into 1 minus QB which is equal to del of r. Okay, so you will get del of AB is less than equal to del of r. Again contradiction, because you have supposed कि del of r is less than del of AB. The contradiction आ गई ਤੁਹਾਡੇ ਕੋਲ ਇੱਥੇ फिर तो. Okay, so B must be a unit. Now converse part is easy. If B is a unit, then del of AB is less than equal to del of A, B, B inverse, which is less than equal to del of A. Also, del of A is always less than equal to del of B, AB. So, both will imply del of A equal to del of AB. Okay. Alright. Third is again trivial. Now, if A is associate to B, so there exists U such that A is equal to BU. U is a unit. Okay, U is some unit. Now, del of A can be written as del of BU, which is greater than equal to del of B. Also, del of B now third property tells you that if A is associated to B, then they are equal. Now, since U is a unit, so del of A is equal to del of B. Okay. Del of B is equal to del of B. Wait here. Also, since U is a unit, so 2 implies del of B is same as del of BU. Okay, which is equal to del of B. So done. Now fourth. So let A divides B, which implies there is some C such that B can be written as AC. Therefore, del of B will be less than equal to del of AC, will be greater than equal to del of A. But we are given that del of A is equal to del of B. Since del of A is equal to del of B, therefore del of A is equal to del of AC. Okay, which gives you that C is a unit. So B is associated to A. From where? From second one. Okay, from second point. Here also from second point. Okay, now fifth, let me give you one example where the converse of second is not true, that if the valuation is same, then they need not be associate. Consider again the Gaussian integer. Okay, you know del of A plus iota B is A square plus B square. So let A is equal to 2 plus 3 iota and B is equal to 2 minus 3 iota. Then clearly A del of A is equal to del of B, which is equal to how much? 16? 13. Okay, which is equal to 13. But we have seen that plus minus 1 or plus minus iota are units in z iota are the only units. So the associates of 2 plus 3 iota are 2 plus 3 iota itself, then you multiply it with minus 1, 2 minus 3 iota. When you multiply it with iota, so you will get minus 3 plus 2 iota, and also you will get 3 minus 2 iota. So nowhere you will get 2 minus 3 iota. Okay, so A is not associated to B. So valuation does not imply that associativity is there if the valuation is equal. However, the converse is true, that if both are associates, then their valuation must be same. Okay. Now next result is important one. Every ED is PID. Every Euclidean domain is principal ideal domain. So let us try to prove it. So let R be an ED with valuation delta. So let I be an ideal. We have to prove that this ideal is generated by a single element. Yani कि this ideal is a principal ideal. Now first of all, if this ideal is 0, then it is generated by 0 ideal. So we are 3. So claim ki apna claim is I is principal ideal. Then I is generated by 0. So done. So we are done. Therefore, we have to suppose I is non-zero. So there exists a non-zero element A belongs to I such that delta A is the least. For all A belongs to देखो, since delta takes and every element to some non-negative number, okay, and non-negative numbers have well-ordered property. Non-negative integers have well-ordered property. Well-ordered property matlab you can find a least among them. Okay, take any subset of a natural numbers, you will always get least number out of them. Okay, so that is called well-ordered property. Therefore here you can also, so it is well-ordered property of n union 0. Okay, n union 0 यानी कि तुसी लीस्ट एलिमेंट लभ सकते हो हमेशा. So our claim will be I is generated by this ideal A. Okay, ਯਾਦ ਹੋਏਗਾ ਤੁਹਾਨੂੰ ਜਿੱਦਾਂ ਆਪਾਂ fx ਨੂੰ PID ਬਣਾਇਆ ਸੀ f ਫॉर ਫੀਲਡ ਲਈ, ਜਾਂ zx ਨੂੰ ਬਣਾਇਆ ਸੀ ਫੀਲਡ, zx ਦੇ ਵਿੱਚ ਕੋਈ ਆਈਡੀਅਲ ਲੈ ਲਿਆ ਸੀ ਔਰ ਫਿਰ ਉਸ ਦੇ ਵਿੱਚ ਇੱਦਾਂ ਦਾ ਐਲੀਮੈਂਟ ਲਿਆ ਸੀ ਜੋ ਕਿ ਲੀਸਟ ਹੋਵੇ। ਓਕੇ, ਇੱਦਾਂ ਹੀ ਇੱਥੇ ਲੀਸਟ ਐਲੀਮੈਂਟ ਵਿਦ ਦ ਹੈਲਪ ਆਫ ਡੈਲਟਾ ਲੈ ਰਹੇ ਹਾਂ। Now clearly the ideal generated by A is contained in I because A belongs to I. Now for any x belongs to I, there exists some Q and R such that x can be written as A Q A plus R. Okay, where delta of R is 0 or delta of R is less than delta of A. Okay, but delta of R less than delta of A is not possible because A is such an element for which delta is the least in I. Okay, therefore R must be 0. So x is AQ, which implies x belongs to the ideal generated by A. So I is contained in ideal generated by A. Therefore I is actually, therefore every ideal is a principal ideal. Every ideal is a principal ideal. Okay, now we need to show that it contains a unity also. It contains a unity also. Okay, so in order to show R is PID, only left to show that R contains a unity. Now again consider B belongs to R such that delta of B is least. Okay, then by above observation every element of R can be written as B times Q dash for some Q dash. Okay, this implies B itself can be written as B times E. Okay, for some E belongs to R. Now for any I, for any I belongs to any Y belongs to R. So Y is BZ again for some Z belongs to R. Okay, now Y times E is BZ times E, which is BE times Z, which is BZ, so which is Y. Therefore E is a unity. Okay, E is a unity in R. hence R is PID. Hence R is PID. Okay. So every Euclidean domain is a principal ideal domain, but remark, not every PID is ED. Okay, not every PID is ED. Example, you just remember it. So R, so A plus B by 2, 1 plus square root minus 90. Okay, so consider such a ring. A and B are integers. This is PID but not ED. Now proof is not very easy to show, and you can just remember it. A plus B by 2, 1 plus square root minus 90. Because those easy examples won't work. Okay, if you see Z is a PID, it is ED also. Just think about Fx, where F is a field, it is PID, it is ED also. Okay, so you won't get an easy example of for which R is PID but not ED. So you must have some non-trivial example, and this example works. So ED is a PID, it means if a ring R is not PID, it cannot be ED. Okay. Alright. So next I'll start with unique factorization domains. Which are also known as UFDs. Okay. So what is the definition? An integral domain with unity is called So keep in mind that principal ideal ਦੇ ਵਿੱਚ ਵੀ ਆਪਾਂ ਇੰਟੀਗਰਲ ਡੋਮੇਨ ਲੈਣੇ ਵਿਦ ਯੂਨਿਟੀ, ਔਰ ਯੂਨੀਕ ਫੈਕਟਰਾਈਜੇਸ਼ਨ ਦੇ ਵਿੱਚ ਵੀ ਆਪਾਂ ਇੰਟੀਗਰਲ ਡੋਮੇਨ ਵਿਦ ਯੂਨਿਟੀ ਡੈਫੀਨੇਸ਼ਨ 'ਚ ਲੈਣੇ, ਬਟ ਯੂਕਲਿਡੀਅਨ ਡੋਮੇਨ ਦੇ ਵਿੱਚ ਆਪਾਂ ਜਸਟ ਇੰਟੀਗਰਲ ਡੋਮੇਨ ਲੈਣੇ ਆ, ਉੱਥੇ ਯੂਨਿਟੀ ਦਾ ਹੋਣਾ ਨਾ ਹੋਣਾ ਜ਼ਰੂਰੀ ਨਹੀਂ। ਓਕੇ, ਇਸੇ ਲਈ ਪ੍ਰੀਵੀਅਸ ਪ੍ਰੂਫ ਦੇ ਵਿੱਚ ਆਪਾਂ ਨੂੰ ਪ੍ਰੂਵ ਕਰਨਾ ਪਿਆ ਸੀ ਕਿ ਅਗਰ PID ਹੈ, ਅਗਰ ਉਹ ED ਹੈ ਤਾਂ ਉਸ ਦੇ ਵਿੱਚ ਆਟੋਮੈਟਿਕਲੀ ਯੂਨਿਟੀ ਆ ਜਾਏਗੀ। ਓਕੇ, ਡੈਫੀਨੇਸ਼ਨ 'ਚ ਲਿਖਣ ਦੀ ਜ਼ਰੂਰਤ ਨਹੀਂ ਹੈ, ਬਟ ਦੇਅਰ ਇਜ਼ ਏ ਯੂਨਿਟੀ। ਸੋ ਐਨ ਇੰਟੀਗਰਲ ਡੋਮੇਨ R with unity is called unique factorization domain if so there is, you must know factorization theorem or fundamental theorem of arithmetic. What is fundamental theorem of arithmetic, or you can call it factorization theorem? It says that you have any positive integer or a natural number, then it has a unique factorization into primes. याद है ना? So now unique factorization into primes, okay, and you are talking about here unique factorization, so there is some relation between them. So instead of primes we will have irreducibles. Okay, instead of primes we will have irreducibles, because in an integral domain every prime is irreducible. Okay, in an integral domain every prime is irreducible. Okay, so let's see. So what is the first? So each non-zero non-unit element of R is expressed as finite product product of finite product नहीं product of finitely many irreducibles. And second, this expression is unique up to associativity and order. If A is P1, P2, Pn and B is Q1, Q2, A is Q1, Q2, Qm are two expressions of A as a product of irreducibles, then this number m should be equal to n, and Pi is associated to Qj for some j. For each I, Pi and Qj's are associates. Okay, यानी कि this factorization in one is unique up to associativity. That is what we mean by unique factorization domain. So again, example Z is the example always. So by fundamental theorem of arithmetic, fundamental theorem arithmetic positive numbers लई है. So every positive integer can be written uniquely as product of primes, and in Z primes are irreducible. Okay, similarly it can be done for negative numbers. जिथे नेगेटिव है किसी भी प्राइम नो नेगेटिव ले लो. ओके, सिमिलरली दिस, क्योंकि जनरली प्राइम नंबर्स पॉजिटिव नंबर्स ਨੂੰ ਕਹਿੰਦੇ ਇਸ ਲਈ ਉੱਥੇ irreducible ਕਵਾਂਗੇ. ओके, सिमिलरली दिस एक्सप्रेशन या इदां लिख लो कि if n is a negative integer, then n is equal to minus of m for some m positive integer. So m has a unique p1, p2, pn, unique up to associativity. Now n is minus p1 p2 pm. Okay, now minus p1, these are also irreducibles, okay. Second example, z with square root minus 5. Now this example has been in our course many times. But this will not work here. It is not a unique factorization domain. It is not a UFD. Okay. ਮੇਰੇ ਖਿਆਲ ਨਾਲ ਆਪਾਂ ਦੇਖਿਆ ਸੀ ਇਹ PID ਨਹੀਂ ਹੈ ਨਾ, ਬਟ PID ਨਹੀਂ ਹੈ ਤਾਂ ਇਹ ਇਕਲੀਡੀਅਨ ਡੋਮੇਨ ਤਾਂ ਨਹੀਂ ਹੋਏਗੀ, UFD ਬਾਰੇ ਗੱਲ ਕਰ ਸਕਦੇ, ਬਟ UFD ਵੀ ਨਹੀਂ ਹੈ। ਕਿਉਂ? ਬਿਕੋਜ਼ 9 has two expressions. 9 is 3 into 3, also it is equal to 2 plus square root minus 5 into 2 minus square root minus 5, and this 3 and 2 plus minus square root minus 5 are irreducibles. ये तुसी देखा सी are irreducibles. So 9 has two expressions where 3 is not associate to 2 plus square root minus 5. Okay, associate भी नहीं है. So two different expressions as a product of irreducibles. ठीक है, ਤਾਂ ਤੁਹਾਡੇ जो z square root minus 5 है ये UFD नहीं बनता. Third is every field will be UFD because you know all the elements are associate. Okay, all non-zero elements are associates. ਤਾਂ ਤੁਹਾਨੂੰ ਪ੍ਰੋਬਲਮ ਹੀ ਨਹੀਂ ਹੋਏਗੀ, ਹਰ ਇੱਕ ਐਕਸਪ੍ਰੈਸ਼ਨ ਯੂਨੀਕ ਹੀ ਹੋਏਗਾ. ਇਟ ਇਜ਼ ਅ ਟ੍ਰਿਵੀਅਲ ਐਗਜ਼ਾਮਪਲ. ਨਾਓ we proved that in a PID every element is irreducible if and only if it is prime. PID ਦੇ ਵਿੱਚ ਇਹ ਪ੍ਰੂਵ ਕੀਤਾ ਸੀ, ਹੈ ਨਾ. ਐਂਡ every ED is a PID, ਸੋ ਇਹ ED ਦੇ ਵਿੱਚ ਵੀ ਟਰੂ ਹੋ ਗਿਆ ਕਿ primes are irreducible, irreducibles are prime. ਹੁਣ let us see ਕਿ ਕੀ ਇਹ ਚੀਜ਼ UFD ਦੇ ਵਿੱਚ ਵੀ true ਹੈ. So proposition is in a UFD an element is prime if and only if it is irreducible. Okay, ਤਾਂ ਇਹ ਕਹਿਣਾ ਚਾਹੁੰਦੇ ਹੈ ਕਿ UFD 'ਚ ਵੀ ਇਹ ਚੀਜ਼ ਟਰੂ ਹੈ ਕਿ ਪ੍ਰਾਈਮਸ ਇਫ ਐਂਡ ਓਨਲੀ ਇਫ ਇਰਰੀਡਿਊਸੀਬਲ. ਸਿਰਫ ਇੰਟੀਗਰਲ ਡੋਮੇਨ, ਮਤਲਬ ਅਗਰ ਤੁਸੀਂ ਇਕੱਲੀ ਇੰਟੀਗਰਲ ਡੋਮੇਨ ਲੈ ਰਹੇ ਹੋ ਫਿਰ ਨਹੀਂ ਉਹਦੇ 'ਚ ਇਫ ਐਂਡ ਓਨਲੀ ਇਫ ਟਰੂ ਹੁੰਦਾ. ਪ੍ਰਾਈਮ ਤਾਂ ਇਰਰੀਡਿਊਸੀਬਲ ਹੋ ਜਾਂਦੇ ਆ ਬਟ ਇਰਰੀਡਿਊਸੀਬਲ ਪ੍ਰਾਈਮ ਨਹੀਂ ਹੁੰਦੇ. ਓਕੇ, ਉਹਦੀ ਐਗਜ਼ਾਮਪਲ ਸੀ ਕਿ 3 ਹੈ ਨਾ, ਕਿ 3 ਜੋ ਹੈ ਜਦ ਤੁਸੀਂ ਉਸ ਨੂੰ ਲਿਖਦੇ ਹੋ as product of 2 plus minus square root minus 1. Okay, product of 2 plus minus square root 1 तो नहीं बनता. k ਤਾਂ ਪ੍ਰੂਫ ਕੀ ਹੋਏਗਾ ਇਹਦਾ? Since UFD is ID, okay, integral domain, so every prime is irreducible. We have to prove the converse. So let P belongs to R is an irreducible element. Claim, so irreducible है तो नॉन जीरो नॉन यूनिट होएगा. क्लेम की है कि P is prime. तो प्राइम प्रूव करने ही अपन लेना पड़ेगा कि P divides AB, and we will prove that P divides A or P divides B. ठीक है. Then AB is P times K for some K belongs to R. Okay. Now if so there are few cases, let me explain it. Case 1, if A is a unit, then B can be written as A inverse PK. Okay, that is B is P times A inverse K, which implies P divides B. Okay, or case 2, similar, B is a unit, then P divides A. तो इन्हां दोनों केसेस तो P किसी ना किसी ਨੂੰ डिवाइड करेगा. ਹੁਣ ਆ ਜਾਓ केस 3 ਦੇ ਵਿੱਚ. So neither A nor B is a unit. Now we are in UFD, okay? So then K is also non-unit. From this equation 1, K is also non-unit. Because अगर K यूनिट हो गया तो ਤੁਹਾਡੇ ਕੋਲੇ या तो फिर A यूनिट आ जाएगा या फिर B यूनिट आ जाएगा. ओके, क्योंकि then because if K is a non-unit, if K is a unit, then P can be written as ABK inverse. Okay, and since P is irreducible, so one of them has to be unit. One of them, A or B, has to be unit, which is not the case. Okay, which is not the case. Now A, B, K are non-units. So we are in UFD, therefore every element can be written as product of irreducibles. P1, P2, P3, Pm. B ਨੂੰ ਲਿਖ ਲਓ Q1, Q2, Qn up to n, और K ਨੂੰ ਲਿਖ ਲਓ R1, R2 up to RT. Okay, where Pi's, Qi's and Ri's are irreducibles. Okay, and these and above expressions are unique up to associativity. Unique up to associativity. This implies from 1, so P1, P2, Pm into Q1, Q2, Qm is P times R1, R2, RT. Now all are irreducibles. So P must be associated to Pi or Qj for some I or K. Okay, क्योंकि दो एक्सप्रेशंस है प्रोडक्ट ऑफ इरिड्यूसिबल्स ਤੁਸੀਂ UFD ਚੋਂ ਤਾਂ ਉਹ ਅਪ ਟੂ ਐਸੋਸੀਏਟਿਵਿਟੀ ਹੋਣੀ ਚਾਹੀਦੀ ਹੈ. ਓਕੇ, ਸਪੋਜ਼ Pi is P times U and Qj is or okay, or Qj is P times U prime. U and U prime are units. This implies that P divides Pi or P divides Qj, then P divides A or P divides B. Okay, so P is a prime. Okay, so I'll stop here today. कोई डाउट हो तो मैंने पूछ लिया.